Let's continue with our remaining two fitness values, the area footprint and the shortest distance. So let's copy our expression we used in the previous lesson to normalize our values, because we're going to use the same expression. Let me disconnect the inputs. Now, like I mentioned in the ending of the previous lesson, instead of maximizing this fitness value, we want to optimize for an amount of square meters we specify. In our case, it's 1,000 square meters. So what we're going to do before inserting our fitness value into the A, like we did with the view quality, we're going to use another expression. And with this expression, we're going to find the distance away from the 1,000 basically. So we're going to do that by, again, using the absolute expression. So we want the input minus AY, and AY is going to be the 1,000, or the value you want to optimize for. So let me also change the inputs. So it's A and AY. So let me insert a slider with 1,000. And let me insert the 1,000 into the AY. Also, let me insert a panel, so we see what's happening. Let me copy this one over. So what this basically does is just measure the distance away, or the amount I'm away from the value I want to optimize. Because if I use 1,000, it's 0. But if I go lower, let's say the square meters is going to be lower, let's say, I don't know, 453, you see that the difference is 547. And of course, that value is going to increase at the lower I get. And if it's 1,000, it's going to be 0. So the output of this one, that one's going to go into the A, like this, instead of directly using the fitness value. So if we're going to look at the AX and the AY, so the minimum is going to be a tolerance we're going to specify from the 1,000. So let me insert a panel and specify 1,000. Let me also set it to multi-line data. Nice. So let's insert a slider with 0.05, which is a tolerance of 5%. So if I multiply 1,000 by 5%, the result is 50. And 50 is going to be our tolerance. So if I have 950 or 1,050, if the value lies within that, I still want it to be output 0. So that's the whole idea, that if the value is within the certain tolerance, I don't want to penalize. So 50 is going to go in the AX because that's the top bound. And the AY, that's going to be the maximum the minimum footprints can have. And that is more or less 200. So 200 is going to be the maximum, which means that 1,000 minus 200, which means 800. So 800 square meters, that's basically the lowest value a footprint can have. And the way we're going to retrieve that value is simply by multiplying our 1,000 by 0.2. Now you can increase or decrease this value. Like I said in the previous lesson, finding the accurate range is very important to get the final fitness value. You don't want to make this range too big because then the impact will be less. But also you don't want to make it too small because then the impact will be increased. So it's a little bit of a play with the 0.2. So let me insert a panel to see what's going to happen. So the reason why this is not 0 is because we have specified 50 as our tolerance. So it will return 0 if I get to 950 or 1,050, if I show that quickly to you. So let me insert 1,100. So if I use 1,050, you see that it's 1, because we're not going to maximize this value, but we want to minimize it. So instead of using the AY, we need to use the AX. It's my bad. So now we have 0, as you can see. And it will also get to 0 if I reach 950. If it's correct. Nice. If this value is getting lower, so our footprint square meters gets lower, you see this value increasing. And it gets to 1 if I reach, if I'm not mistaken, it's going to reach 1 when I'm reaching 800. There's just one problem. What I want is that if my value lies within 950 and 1050, I also want this value to be 0. Because look, if I go from 950 upwards, you see that my value increases again. So we need to rewrite our expression a little bit. Now the way we're going to do that is by adjusting this expression here. Let me open it. So instead of using the absolute value we get by subtracting AY from A, we're going to use an if statement. An if statement is really nice because it allows us to have a condition and then output a value if that condition is met. And if the condition is not met, output a different value, whatever you want. Our condition is going to be if this value is lower or smaller than our AY times our tolerance, which is 50, as you can remember. We want to output that value, so AY times our tolerance. And if the value is not met, I just want to output what we got from the beginning, which is the absolute value of A minus AY. So that's the whole idea. So, of course, we need to insert the tolerance input here. Now that tolerance is 0.05. Nice. So if I insert a panel, this will just output the difference from 1000 basically. But if I reach the tolerance, which was 950, right now you see that it just stays at 50. And that's exactly what we want. And if we surpass our 1050 again, which is the bottom limit, you see that now it increases again. So that's nice. That's exactly what we want. Because it outputted the 50, you see that here it stays at 0. Let me drag this one a little bit here so it's more clear. So it's 1 at 800. It's still correct. Yeah. And then if I go up all the way until 950, like here it stays at 0. Because now my value, my square meters, is within the bounds we specified, our tolerance of 5%. Nice. So now let's connect our area footprint to here. Let me connect 1000, the panel to here. Let me rename this to amounts of square meters to optimize for. Like that. So let me rename this one to tolerance. Nice. So that was the area of the footprint. And the last one is the shortest distance. And we're going to use more or less the same trick. So we need to copy this one over. Let's disconnect it. And before I forget, like this one we want to minimize it, but this one we want to maximize it again. So we need to change this one into AY. The same as with our view quality. And we're going to use the same trick. So let me insert an expression. And let me also insert a slider of, let's say, 50. So let me copy this one over. So the minimum a distance can have, that's 0. And I know that for sure because the buildings, they can really stick to each other. But the maximum, I'm not sure about that one. But that's actually a value we're going to specify. Because like I mentioned in the previous lesson, let's say I want to start penalizing if a value is below 15 meters. So let's set 15 meters as our minimum distance. So I know for sure that these values, they're going to lie between 0 and 15. Yeah, if it's 0, this output will be 1, which is the worst case. And if it's 15, this output is going to be 0. So that's great. The only thing is that if this value increases, this value also increases, but I don't want that because for me, everything that's above 15, the buildings are far apart. So I just want it to be outputted 0. And that's what we're going to do with the part in the front. It's a little bit the same like we did with our footprint. So we're going to write again an expression, an if statement. So what I want is if x is smaller than y, I want to output x, and if not, I want to output y. Now x is going to be our distance, and y is simply going to be our 15 meters. Let me drag everything a little bit here. So let me insert a panel to see what happened. Let me use a slider for this one. Nice. So if my value is lower than 15, you see that it just gets passed through. But if it's above 15, it will just output 15. Like it doesn't matter what it is. And that's exactly what we want. Because if I now connect this output to the A, you see that this value stays at 0, which is exactly what we want. But as soon as it drops below 15, you see that this value increases. So the x input is the shortest distance. Perfect. So now we have our 3 values, which we got here. These are our 3 not normalized fitness values, but here, after this one, they're all between 0 and 1. So the only thing we need to do now is to add them all together. We can use a simple addition component for that. So let me show a panel. Yeah, so these are the final 4 fitness values for the 4 footprints. The only thing is Galapagos can't optimize different branches. What it will do is that it will average this number, so it will always have one number to optimize. Let's just get the average of these 4 numbers. There are different ways to do this. What you could also do is get the worst value, which is the highest value, and just use that one to optimize for. But let's for now just use the average. Let me insert a number component. And let me just call this fitness value for Galapagos. Great. So let me insert the Galapagos component. So the fitness value is this one. And the genomes, those are all the way in the beginning. We specified, so those 4 or 6 gene pools. So hold shift to connect multiple. So we start with this one. Hold shift to connect the next one, etc. Nice. So that's the whole setup to get started with Galapagos. In the next lesson, we're going to run some simulations and see the result. And also, this marks the end of the first part of this course. The second part will consist of tweaking the definition and make it better to work with Galapagos so we get more optimal results. So I hope this lesson was clear, although I went pretty quickly through all the definitions and the expressions. I would invite you to try around the definitions with individual sliders to see for yourself what happened and what you will do if you increase a number or decrease a number. Always keep in mind that we're optimizing for 0. So thank you so much for watching, and in the next lesson we're going to tweak our definition to make it better to work with Galapagos. Thank you.